Alright, welcome to video 7. Calling this one Why Gain, because we're going to learn what a gain control is, gain controls, why we have them, how to set them, what's going on with them. First thing we're going to do is answer the homework problem from video 6. It's been a minute since we did video 6, sorry about that, we've been pretty busy around here. But let's go ahead and solve this. The question was, on video 6, is we have this amplifier driving this reactive load. It's more like a speaker would be. This is a very simplified version. And the question is, what's the true power? If we put a clamp on here and a voltmeter, what will we measure on the clamp versus what is the actual true power that the amplifier is putting out? So, first thing we need to do is we need to figure out, we have 100 volts peak, so we need to convert that to RMS. So, we'll do that first. 100 volts peak equals 70.7 V RMS. That's just something I have memorized, but we know it because voltage peak divided by the square root of 2 equals V RMS. So that's how we know that. So we have 70.7 volts RMS here. The RMS. So if we were to put a voltmeter across here, we would measure 70.7 volts on the meter. And now we want to find the current. If we were to put a current clamp on here, what kind of current would we see? Well, we know this is 2 ohms, but we need to find the impedance of this capacitor at 50 hertz. Remember, the impedance of capacitors and inductors change with frequency. So the formula for the impedance of that capacitor is XC, or I called it ZC on the other video. Either way, I just didn't want to confuse anything on the other one. It's 1 over 2 times pi times the frequency times the capacitor. So we have XC equals 1 over 2 pi 50, because 50 hertz. And then the capacitor, which is 470 microfarads. So that's 0.123456 would be micro, and it's 470. So it would be right here, like that. So when we figure that out, we're going to see that the impedance of the capacitor at 50 hertz is 6.77 ohms. So we'll put that over here. 6.77 ohms. We also need to know the resistance of the resistor, because these are in series, so the amount of current that this voltage is going to generate is this whole load here. So we know that's 2 ohms, so R equals 2 ohms. And when you have resistors in series like this, or the reactance of that capacitor, the actual formula for it is Z. Z stands for impedance. Square root of this impedance squared plus this impedance squared. So it looks like that. 6.77 squared plus 2 squared, and then the square root of that whole thing. And if you work all of this out, you'll get that Z equals 7.06 ohms. So this amplifier is seeing 7.06 ohms. When you play 50 hertz, it's seeing 7.06 ohms. So then we could figure out what this current is going through here, because the current is just going to be the RMS voltage. So this is the RMS current. RMS current is the RMS voltage divided by the impedance. So that's 70.7 volts RMS over 7.06 ohms. You work that out, it equals about 10 amps. It's like 10.0 something. So we have 10 amps going here. So the clamping, the people that like to clamp to measure power, they're going to take the voltmeter, which reads 70.7 RMS, and multiply it by the current, which is 10 amps, and they're going to say that 70.7 times 10 equals 707. And they're going to say it's 707 watts, which it's not at all. Hopefully we've learned that by now. It's 707 volts times amps, so we call that 707 VA. On a clamp, if you use clamps, you would think you had 707 watts. Okay, so we have 707 VA. Now we have to figure out the phase angle of the voltage and the current, because since there's a reactive load in here, the volts and the amps aren't happening at the same time, they're offset in time. If you see all of video 6, you understand why that's happening. So the formula for that is the phase of this situation is going to equal the inverse tangent, you have to find that button on your calculator somewhere, of the impedance of the capacitor divided by the impedance of the resistor. So it's the inverse tangent of 6.77 over 2. Once you figure all that out, you're going to see that the phase equals 73.54 degrees. So the voltage and current coming out of here are offset by 73 degrees. That's quite a bit of an offset. And then we know that, or we've learned that actual watts is going to be the VA times the power factor. Well, the VA, we already figured it out right here, 707. So the actual watts is 707 times the power factor. What's the power factor? Well, the power factor, you have to know this phase. That's why we figured it out. So the power factor is the cosine of the phase. I don't know what that says. It's supposed to say phase. Cosine of phase. So once we calculate that, the cosine of 73.54 degrees, we see that the power factor is 28.3%. So 707 times 28.3%, work that out, and we see that the actual watts, 200 watts. So the answer to the homework, we asked a couple different things. One of them was, what's the voltage, the RMS voltage? What's the impedance of the capacitor? What's the impedance of the whole system? How much power do you think you're getting if you're using clamps? Right here, 707. And then the phase angle, 73 degrees. The power factor, 28.3%. And finally, the actual power that's happening, only 200 watts. So there you go. Hope you guys had fun with that and learned some stuff. And let's talk about why gain. Right, let's talk a little bit about gain and why we need gain and what is gain. Well, when we say the word gain, what we're talking about is voltage gain. So that means, let's say we have this little black box here and it has a gain of 10. What that means is if I put 1 volt in here, then I'll get 10 volts out. It's a gain of 10. If this was 5 volts in, I would get 50 volts out. It's like a multiplier, so it's going to multiply it by 10. This is what an amplifier does. This is exactly what an amplifier does. You put in some low-level signal from your head unit, and it gains it up to some large voltage that can drive your speakers. So let's take a closer look. So here we have our head unit, and the head unit is connected to the vehicle's 12-volt system and ground. So this is the available power supply that the head unit has to work with. And in engineering we call these voltages the rail voltages, because when we're going to draw the signal, it kind of fits, it has to fit in between here. We're not going to have a signal less than ground or more than 12 volts that can come out of here, because this is the available power that the head unit has to deal with. So when you draw them, and if I say this is 12 volts and this is ground, you know, it looks like rails, like for a train or something. So it's kind of where the name came from. So the rails in the head unit are 12 volts and ground, and we're trying to fit our audio signal in here. Well, audio signals go positive voltage and negative voltage. That's why a speaker moves out and then back in. To generate a sound wave, you need to do both. Well, the head unit doesn't have a negative voltage, so what happens is we what's called bias the audio signal up so that it's halfway in between the rails, halfway in the middle. So 6 volts. So inside the head unit there's some biasing that takes the audio signal and lifts it to here, so when there's nothing coming out of the head unit, the volume's all the way down, it just has this 6 volts DC where the signal would be. It doesn't come out the RCAs because at the end, if this was the actual output, they put a capacitor here so that capacitors block DC. So it would block all the 6 volts out, and the only thing you would get is the AC voltage coming out of there. So, but inside the head unit, this is what's going on. So we have these rails. 6 volts is going to become our ground, if you will, or our center point, and we're going to try to fit an audio signal within this window. If the audio signal gets too big, then of course it's going to clip. That's what clipping is. When you hit the rails, the sine wave that would be here and would be here gets clipped off. That's why it's called clipping. Okay, so basically we have this small little window to work with here. If we were to calculate the RMS of this signal, you can see that the maximum signal that we could fit in here would be from 6 volts to 12 volts, or from 6 volts to ground. So we have a 6 volt plus and minus 6 volt window here. So that would be a 6 volts peak. So the sine wave that would fit inside of here has a peak of 6 volts, because this is 6 and this is 12, so the difference is 6 volts peak. Well, 6 volts peak, if you convert that to RMS by doing this, it's about 4.2 volts RMS. And now you know why every head unit puts out 4 volts. There's nothing special. It's just how it happens because it's on a 12 volt car. There are some head units that only put out a volt or two because I don't know why. They have some cheap parts inside that can't make it all the way to the rail, if you will. This would be called like a rail to rail output, because the output device in here that drives the RCAs is good enough that it's able to push the signal all the way close to the rail and close to the rail. This is a best case scenario. You know, we're going to end up with about 4 because we're not going to get all the way to the rail. And like I said, some lesser head units will have some lower quality stuff in there, and they might only have 3 volts out or 2 volts out or something like that. But that's what's going on inside the head unit. That's why it puts out 4 volts. And now we need to somehow get this to our speaker, and 4 volts isn't going to be enough, so that's what an amplifier does. It gains the signal up to something large. So let's take a look at that. Okay, so let's assume we have this head unit that puts out 4 volts RMS, and we're going to connect that to our amplifier that is 1,000 watts at 1 ohm. 1,000 watt at 1 ohm monoblock. This amplifier has a gain knob on it. Why does it have the gain knob? Well, if this amplifier is 1,000 watts at 1 ohm, if you do the math on this, that works out to 31.6 volts RMS output. So this amp, the input to this amp is 4 volts RMS on the RCA, the maximum, and the output needs to be 31.6 volts to get the 1,000 watts out. So the amplifier inside has a power supply. We've got our 12 volt connection from the car and ground, and inside here there's a power supply in here, and that power supply puts out some higher voltages. It takes the 12 volt and creates higher rails. So the rails for this amplifier, this is a real power supply, so it doesn't have that center issue where it's like half of a voltage. The center is actually ground on an amp with a power supply like this. So this is 0 volts. If you want to fit a signal that's 31.6 into here, where do we have to put these? Well, they have to be able to fit the peak of this. So 31.6 volts RMS times the square root of 2 will give us the peak, and if you work that out, we'll see it's about 45 volts. So these rails here are 45 volts and minus 45 volts. This is the output. This is what connects to our speakers. So now we can fit a signal in here much bigger than the little 4-volt RMS signal. We can fit this signal that goes all the way from 0 up to plus 45 and down to minus 45. We get this big signal in here, 31.6 RMS, and do a 1 ohm load. We can get 1,000 watts out of this thing. Well, if there's 4 in and we need to get this out, then the gain needs to be 31.6, which is the output of the amp, divided by the 4-volt input to the amp on the RCA. Do the math on that, we'll see it's about 8. So the gain needs to be 8. Well, amplifier manufacturers don't label their gain knobs that way. They'll either say min, max, or they'll have some random numbers, you know, 1 to 10 or 1 to 11 because they think they're being funny. Or they'll do it backwards and confusing, like they'll put 4 volts over here and then like half a volt over here. I mean, technically it kind of makes more sense because you have a bigger, you know, head unit that can put out more voltage, so you wouldn't need as much gain. So I mean, I understand why they do that, but still, I feel like it'd be nicer if it just had the actual gain on there. So the actual gain we need to get is 8. So what would happen, this head unit we put, you know, like if you're using our DD1 tool to try to know where to set this, I mean, that's kind of the thing, is this has a certain place it needs to be for this to happen. Turning this up higher isn't going to make us get more than 1,000 watts. It's just going to start clipping the signal. We won't get more than 1,000 watts clean out of it anyways. And if it's too low, then we won't have enough gain and the signal will never get to the rail and it'll just be in here and it'll be too small. So there's definitely a correct setting. On this amp we need a gain of 8, wherever that may be. Let's just say it's here, to do this. So, you know, we could put a DD1 distortion detector on this output of the amplifier, and we can turn this knob up, and as soon as we get past a gain of 8, it's going to start to clip, and the DD1 would show that, would show the distortion. So that's why we need a gain knob. And, you know, because this, if this was a 2-volt head unit instead, then what? Well, then this is a 2, and then this is 16, and then this knob needs to be way over here somewhere. That's what the knob is for, just to, you know, adjust your amplifier for your head unit. So let's take a look at what happens when we have something in the middle, like a processor. Okay, here we are. We have our head unit over here. Little knob, little volume knob. And let's say this head unit puts out 3 volts RMS. And then we have a processor here. Some kind of sound processor. The processors, typically an audio processor will use little amplifiers inside of them called op amps. Stands for operational amplifier. And typically those have those will sit on power supplies that are plus and minus 15 volts. So that's what we're going to assume in here, that this thing has 15 volt rails in it. So here's our head unit over here. It's got 0 and 12 volts because that's what the car's on. It's referenced to the 6 volt center. And then we have our processor over here that's on 15 volt rails. So it's got plus 15, minus 15, and ground. And then we have our amplifier over here, and let's say that this amplifier is the same one, 1,000 watts, and that one had 45 volt rails in it. Plus 45, minus 45, and ground. So let's pretend that we're going to hook up a DD1 or an oscilloscope out here to set the gain on these items. Now this one has a gain control and this one has a gain control. So how do we do this? Well, first we just want to start from the front and work to the back. So first thing we want to find out is how far can we turn this volume knob on the head unit before the signal hits these rails. So we don't have to take the RCAs from here and stick them into a DD1. You know, when we first came out with that product, We thought it'd be useful for processors and things like that, but as it turns out, after it's been in production for a few years and we've used it a lot now, we see that it's just best to hook it up to the output of the amplifier and just leave it here the whole time. So let's say this is our output and here is our DD1 tool. So you put a 0 dB track in. 0 dB means that the signal that's recorded goes all the way up to, it's digital. So digital is a lot of ones and zeros. The highest thing a digital can be is all ones, and the lowest is all zeros. So a 0 dB track means that the sine wave is going up as high as it can go without clipping internally in the digital circuitry. So we put the 0 dB track in the head unit, and we turn the head unit up and up and up. And as we turn it up, the signal that the head unit's putting out is getting bigger and bigger and bigger, and eventually it gets as big as it can get. It hits these rails and it clips a little bit, and when that happens, the distortion detector says distortion. So we back the volume down one click, the distortion goes away because this signal passes through here. Maybe it doesn't have any gain because these gain controls are down, but if we clip it here, it'll be here clipped like this and like this, the same signal. So we got to make sure it's a clean signal. And then once we have the maximum clean signal here, which is going to be sitting here, we start turning this gain up until we can get to the rails in the processor. Eventually we're going to turn this gain high enough where we're going to hit these 15-volt rails, and then we're going to back it down a little bit, make sure that light doesn't come on the DD1, and we're going to find a setting where the signal is now the maximum here, it's the maximum here without hitting these rails, and then we're going to move to this gain. So now we've gained it up from 3 volts RMS to, if you fit in between 15-volt rails, you can get about 10 volts RMS, a little bit more, maybe 10 and a half. Well, we need to get to 31.6 volts RMS. So we still need gain on the amplifier. So that setting goes there, maximum there. This one we turn it up until we reach these rails. And then now this signal is like this. And now we turn this gain up. So that gain, and then this gain, and eventually we'll turn this gain high enough where this one just barely hits the rails. And there we go. It's all set up. So you just work from the front back. Each one of these knobs has a setting that it's supposed to be at. All kinds of wacky things can happen. If this is down and this is too far up, the signal here will be clipped. But the signal here will be clipped and never reaching the rails. So the distortion detector will say distortion because it sees distortion even though it's not hitting the rails. So in this case, you're not getting the full potential of your system. This gain needs to be turned down so that we fit within the rails, and then we can turn this gain up so we can reach the rails, and then we can get the maximum out of that amplifier. The other way around would be if this gain was too low, this signal was too small, and so on this setting here we have to turn this gain really, really high to try to get this small signal big enough to get to the rails, and when we do that we're either going to run out of gain or we're going to end up amplifying any noise that's riding along these RCA cables. So it's very important to set each one of these at the right stage. I hope that explains why we need gain and what gain is and how you work from the front back no matter how many processors you have. You just work from the front back, leave the distortion detector at the end, and you'll find the rails of every component in the chain. You'll get the most out of your system with the least amount of noise. So let's do some homework.